So good evening, ladies and gentlemen. So we were introduced as scientists. I just want to make a point. I'm an engineer. One for the engineers. So what we've got is a situation where we have the scientists that need instrumentation to look at all those fabulous galaxies and stars. And in between, there is this giant piece of engineering. And whether it's a telescope, whether it's the instrumentation, somebody has to build that. So this is what happens at Mount Stromlo. Unfortunately, on the left-hand side, we have that happy scene, lots of trees, nice, pleasant. But in 2003, of course, we all know that that's what happened on the right-hand side. But wait, there's a silver lining. So here you have a series of workshops which were designed in the 80s, in the 60s, to accommodate the instrumentation for telescopes that were up to maybe 4 meters in diameter, and we were able to stretch the capacity of those workshops to deal with instrumentation for telescopes up to 8 meters. However, lightning struck and we were destroyed on 2003. But look, lo and behold, there's a new facility that was developed out of the ashes where the old workshop used to exist here. A combination of the fire, destroying what we had, dam, insurance, largesse of the university, and a kind donation from the federal government, and we were able to build at least this first half of the complex now known as the Advanced Instrumentation and Technology Center at Mount Stromlo. But it's a complicated story to tell because Professor Penny Sackett, who is actually here, hand up Penny, where are you? There you are. Penny had the unfortunate situation where she had really only just joined as the director of Mount Stromlo, and then we had the fires. Well, that was terrible. However, at the same time, the astronomers had developed the next decadal plan, which said Australian astronomers wanted to be part of an extremely large telescope, a giant segmented, multi-segmented telescope, a GMST. As it turned out, the Giant Magellan Telescope was the best fit for us. So the result was that in 2006, the AITC was scaled because we had to build a new facility. We had to replace that existing burnt workshop. We scaled it to fit the instrumentation that would be required by giant telescopes, these ELTs. Then, at the same time, the ANU invested in the Giant Magellan Telescope that put our peg in the ground. Astronomy Australia Limited found an extra $5 million, added it to our contribution, and then in 2009, an $88.4 million Education Investment Fund grant was raised. The Australian GMT Project Office happened, and we were off and running. And we're running towards, in fact, extending the AITC to the second stage, AITC2, and all the test facilities that are in there, and all of the GMT projects that were coming out of that, including adaptive optics, instrumentation. And today, if you come up to Mount Stromlo, and I know that not many of you have, but if you do, you'll see this wonderful architecturally designed building. You let an architect do it. As an engineer, it's not a good idea. But it did look pretty good. And it's supposedly far more fire tolerant than the old one was. But today, we are this complex of, 30 engineers and scientists that we're seen as a unique national asset. And I'll explain why in a moment. And that asset supports astronomical instrumentation, space systems, research and training, and we serve the entire astronomical research community. It's not just the ANU's playpen. It is for the whole of Australia, Australian industry, defence, and we support international collaboration as a result of that. So, to give you an idea of some of the things that we're doing here, we have this list of current projects. So the integral field spectrograph, this is Rob Sharp's instrument, the GMT, laser tomography, adaptive optics, lovely acronyms. AO for space debris tracking, which Francois was talking about. This means that we can actually see space debris now down to not large pieces, but down to a few millimeters or centimeters. And that means that you can start to track this debris. And, you know, there's probably a couple of $1 billion worth of space assets orbiting our Earth, providing us with space-based information. So if a piece of junk hits one of those assets, and it's traveling at about 7.5 kilometers a second, it packs a punch. So it's really good to know if you're about to get hit, and if you can move out of the way, fine. If you can't, hunker down, hold your breath, and say a prayer. We're also doing other AO work for other organizations, for the Gemini telescope. We're part, as I said, we're in a collaboration with industry, so we're working with electro-optic systems on a AO-based enhancement of a telescope for South Koreans. Veloce spectrographs and more spectrographs that we're building for other instruments and other telescopes. Again, software project Ghost for Gemini. These are things that are standard in the engineering of space instrumentation. But what's really cute is now we're moving into this class of CubeSat mission. So CubeSats are a tiny research class of satellite that is 100 centimeters by 100 centimeter cubed. And you can stack them together. And as you stack them together, you also start to get more capacity and capability. They're designed as a research tool that very easily allows the universities of the world, which don't have a lot of money, most universities don't have a lot of money, to actually build small scientific projects and get them into orbit easily. So, our facilities are facilitating that capability. We're also part, as Francois had already said, of the CERC AO Research Center. So a couple of prospects that we've got in waiting at the moment. Another potential contract for the South Koreans, but this one's really cool. This one's really cool because it is what is called the 6U CubeSat, which will have an astronomical instrument on board for space-based astronomy. This is the first time that Australia will be proposing a CubeSat mission through the Australian Research Council's LEAF competitive research project funding process. And we're part of 11 national and international partners, and much of that will be centered on Mount Stromlo. A lot of it will be centered on John's location at the AAO, and this is a real stepping stone. It's a step change for Australia, and all of us have got our fingers crossed to make sure that that comes through. So a little bit more bragging, I guess, and forgive me for the bragging. But the AITC houses the headquarters for the Space Environment Research Centre, we know that now. Since 2006, and these statistics were very cleverly put together by Naomi, and they're entirely supportable, aren't they? Yep. The statistics, you know, lies, damn lies and statistics, but these are really good statistics. The AITC has supported, not necessarily directly benefited from, but supported $118 million worth of projects. And of that, some 17 million have been in exports. So this is not just an esoteric scientific mission. This is a program that has stimulated the science, and it will generate science in the future, but it has also generated this facility that is now stimulating industrial participation as well. So the AITC complex is in fact the only end-to-end astronomy and space environmental test facility of its kind in Australia. Now that's astronomy and space. And I'll talk about a little bit why that's relevant. That federal investment has provided a step change in our capability and has now made us a competent collaborator on the international stage. That's very important because we didn't have that capability before, now we do. Now some pretty pictures, enough words. Tools of the trade. So here we have the main integration hall at the AITC. We have an EMC chamber, a small chamber for testing electromagnetic capability. But this is our pièce de résistance, the Wombat XL. Why XL? Because there's a Wombat which is not as big as that, and there's Wombat XL, which is as big as that. So this is a space simulation facility. In other words, we can pump that chamber down to 1/10 of a billionth of an atmosphere, and we can also bring the temperature down to about minus 190 degrees Celsius. We can also bring it up to plus 150 degrees, all in vacuum, all to simulate the extremes of environment that space missions have. Oh, by the way, inside the instrument that we're building, that Rob Sharp's instrument is building, we have to have major subsystems of that operating at cryogenic temperatures in vacuum. So there's a similarity there. But our facilities are not just a thermal vacuum chamber. We now have a vibration test facility, and we're running vibration test courses. And you can see here a whole bunch of happy campers actually on the test rig, not while it's working, obviously. And here they are getting hands-on. So this is like a giant speaker, in effect. It works in exactly the same way. You have an amplifier, you have a signal, you introduce it into an electrodynamic coil and cause the center piston to move at a frequency that you can determine. So it enables us to simulate the vibration of the launch ascent phase of any space mission when it's sitting on top of a controlled explosion, which is known as a rocket. So we've used this thermal vacuum chamber for astronomical purposes as well. You remember Rob showed you that first piece of optics that was built for the instrumentation? Well, that's the team actually testing it in the thermal vacuum chamber. Getting it ready to test, obviously. They'd be rather desiccated if they weren't there. So, just a little bit of a quiz. Did you know that pretty much all modern infrared astronomical instrumentation, to get the maximum performance from those detector and focal plane arrays, they work in vacuum at cryogenic temperatures, and they require specialized materials, special processes, precision integration and test. And so what? Well, it's the same, pretty much the same requirements that space systems have. So what you'll see at Mount Stromlo is that all of our test facilities are actually dual use. That means that we can use them for astronomical instrumentation and systems, but we can also use them for qualifying space systems, because the two are very, very much the same. The only difference is we don't launch the instruments that we build for terrestrial applications. So we talked about international collaboration. We have a lot of collaborators. So this wall, which is a great idea that Naomi put up, shows those people that we're actively collaborating with today. And there's another row that's due to go up here already. So both within Australia and internationally, we are collaborating extensively. And because astronomy is a really very international organization and profession, you get all of the thank yous in the different languages that we deal with. So thank you very much.